Water desalination, chemistry and technology. Water desalination, chemistry and technology. Introduction. Water is a vital resource for sustaining life, agriculture, industry, and various human activities. However, the availability of fresh water is limited, and in many parts of the world, access to clean and safe drinking water remains a challenge. This scarcity of freshwater resources has led to the development and implementation of innovative technologies like water desalination. Water desalination is the process of removing salt and other impurities from seawater or brackish water to produce potable water. This article delves into the chemistry and technology behind water desalination, exploring its various methods, benefits, and challenges. The need for water desalination. As the global population continues to grow and water demands increase, the strain on existing freshwater sources becomes more pronounced. In arid and coastal regions where conventional freshwater sources are limited, desalination offers a promising solution to meet the water demand. Additionally, climate change and its effects on water availability have further highlighted the importance of diversifying water sources. Desalination methods. There are several methods of desalination, each based on distinct chemical and technological principles. The most common desalination methods include distillation and membrane processes. 1. Distillation. Distillation is one of the oldest and simplest methods of desalination. It involves heating saline water to create vapor, which is then condensed back into liquid form to obtain freshwater. This process exploits the differences in boiling points between water and salt. Various distillation techniques, such as multi-stage flash distillation and multi-effect distillation, have been developed to improve energy efficiency and water production rates. 2. Membrane processes. Membrane processes are widely used in modern desalination due to their energy efficiency and versatility. These processes rely on semi-permeable membranes that allow water molecules to pass through while blocking the passage of ions and larger particles. Reverse osmosis, ρ. In ρ, water is forced through a semi-permeable membrane under high pressure. This pressure drives water molecules through the membrane, leaving behind concentrated brine. ρ is highly effective in removing salts, minerals, and other impurities, producing high-quality freshwater. Electrodialysis, ED. ED involves using an electric field to move ions through ion exchange membranes, separating the salts from the water. This process is particularly useful for brackish water desalination and is often used in combination with other methods like ρ. Chemistry behind desalination. The chemistry behind desalination processes revolves around the principles of solubility, ion interactions, and osmotic pressure. 1. Solubility and precipitation. Many salts are less soluble in water at lower temperatures. Distillation takes advantage of this principle by evaporating water and leaving behind the less soluble salts as solid residues. In some cases, these solid residues can be further processed to recover valuable minerals. 2. Ion exchange. Ion exchange involves replacing undesirable ions in the water with more desirable ones. This is often seen in processes like electrodialysis and certain forms of water softening. Cation exchange resins can remove calcium and magnesium ions responsible for water hardness, while anion exchange resins can remove negatively charged ions like chloride. 3. Osmosis and osmotic pressure. Osmosis is the movement of solvent molecules, usually water, through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. Osmotic pressure is the pressure required to prevent this movement and is a critical factor in desalination processes like reverse osmosis. By applying pressure higher than the osmotic pressure, water molecules can be forced through the membrane, leaving behind concentrated brine. Technological innovations. Advancements in technology have led to improved desalination efficiency, reduced energy consumption, and increased water production rates. Some notable innovations include energy recovery devices. These devices help recover energy from the brine stream, reducing the overall energy consumption of the desalination process. Nanotechnology. Nanomaterials and membranes with nanoscale features have enhanced the selectivity and permeability of membranes, improving desalination efficiency. Solar desalination. Solar energy can be harnessed to power desalination processes, making them more environmentally friendly and sustainable. Benefits and challenges. Benefits. Increased water supply. Desalination provides a consistent and reliable source of freshwater in regions with limited access to conventional freshwater sources. Diversification of water sources. By incorporating desalinated water into their supply, communities can reduce their reliance on weather-dependent sources like rainwater and rivers. Agricultural and industrial use. Desalination can support agricultural and industrial activities that require substantial water resources, contributing to economic growth. Challenges. Energy consumption. Desalination processes, particularly RO, require significant energy input, which can contribute to greenhouse gas emissions and high operational costs. Environmental impact. The disposal of concentrated brine back into the ocean can harm marine ecosystems if not properly managed. Cost. While the cost of desalination has decreased over the years, it still remains relatively high compared to conventional water treatment methods. Conclusion. Water desalination plays a crucial role in addressing water scarcity challenges around the world. Through a combination of chemistry and technology, desalination processes have evolved to provide a viable solution for producing freshwater from saline sources.